Hello students. So today we are going to discuss about the Hooke's law. Okay. So as we all know, what is that Hooke's law? The famous Hooke's law is the stress is directly proportional to strain. Stress is directly proportional to the strain. What is stress? Stress is nothing but it is the external force you are going to apply on a body. Okay. The strain is the effect caused by stress. Okay. So how you are going to increase the stress, that there will be a corresponding change in the strain. That is what the famous Hooke's law tells about. So this Hooke's law is valid for load deformation. Okay. So load deformation in the sense certain bodies, if there is a less deformation in the sense, if you apply small stress, there will be a change in the strain. Okay. So low deformation means there will be some molecules, they will regain their original position if you remove the external force. Okay. So under this Hooke's law, you are going to study about two things. One is the elastic materials, the other one is plastic materials, right? So we all know that elasticity is nothing but the external force, the applied force. If you remove the external applied force, the body is going to regain its original shape. So here the objects are going to regain original dimensions, you can call original dimensions. The body objects are going to regain their original dimensions if you remove the applied additional external force. Force is nothing but the stress we are going to apply it on a bodies. Okay. Take for example, if you take a rubber strand of 4 centimeter, stretch it. Okay. So rubber, we know that it is a best elastic material. If you stretch it, so it will extend, right? So if you remove the external force, it will go back to its original length. Say for example 4 centimeter band. So if you apply the stress or the force on the each end, if you stress it, okay, so it will extend in its length, linear length. If you remove it, it will go back to its original shape. Such materials we call it as elastic materials. Okay, the elastic materials are the one which regain their original dimensions, whether it may be the length, breadth or height. Okay, so that is why we call it as they regain their original dimensions. Such materials we call it as elastic materials. Okay, there are another class of materials, they are called as plastic materials. Okay, so we know that this is inverse to this elastic materials. Say for example, instead of rubber band, you take a copper wire, stretch it. Okay, so leave it the additional applied external force, it is not going to regain its original dimensions, right? So such materials we call it as plastic materials. That means whatever the change in the dimensions, it will be a permanent set. Okay, so such materials are called as plastic materials. So in elastic materials, this Hooke's law is valid for lower deformation because the molecules are going to retraced, they are going to regain their original dimensions if you remove the applied external stress, right? So hence the stress is directly proportional to the strain. Okay, so today we are going to study about the famous stress strain curve, right? So we are going to draw how stress is going to affect the strain. Y axis you take a stress is applied on a body. So here the strain is going to be caused due to the stress. Okay, say for example, take some metallic wire. I'll take one example here. So I'll remove this for, okay. So for this additional stress strain curve, we are going to consider the metallic wire. So any metal, you take copper, aluminum, whatever it is. Okay, take metallic wire. We know that all the metals, they show ductile properties. Okay, so such metallic wire, take one metallic wire, on that I am going to apply stress. Stress is nothing but the force. We are going to apply some external force. Stress is nothing but it is force only. Okay, so how we apply the force on the metallic wire and what will be the cause? Strain is the cause of the stress. Say for example, in the beginning, call this as O, right? So here up to here, this point I will call it as A, right? So once you apply stress, there will be continuous strain is produced. Strain is nothing but the effect caused by the stress. Strain is nothing but it is going to change the body dimensions. Okay, we have taken metallic wire, we are applying force. Okay, it is going to change in its length. So this is the original length. Okay, I am applying a stress, I am applying an additional force. The body is going to change its length, say up to point A. Okay, how it is going to vary? It is a linear variation of the strain. Stress is applied continuously, strain is going to vary linearly. Okay, up to point A. So what happens after this point? How it vary? It is not linear. I will call this as point B. Point B is called as proportionality limit. Proportionality limit. Up to point A, there is a linear variation of the strain with respect to the stress. So after point A, if you continue applying the additional stress, the variation of the strain is like this, up to point A to point B. But it is not linear, it is increasing, right? Now, so if further, if I increase the stress, what happens to the body? If I further increase the stress on the body, that is metallic wire, so this point B, it is going to vary like this. So this I call it as point C. Now here is, it is called as the elastic limit, or I can call it as a yield point. Yield point. This is also called as an elastic limit. Okay. So what is that mean? See, up to here, if I increase the stress, the directly strain is going to increase linearly up to point O to A. This is a linear variation of the stress with respect to strain. If I remove, okay, just a minute. Okay, so if I remove the applied stress, so what happens? The body is going to regain its original shape or size. Okay, so we can call it as plastic behavior up to point A and B here. Now next, if I further increase, it will go to yield point. So from yield point, if you want to further increase, the body will reach to its yield, ultimate strength, then it will break. So this I will call it as, for reference, D, and this is E. This D I call it as ultimate strength. Okay, and E is nothing but it is fracture. What do you mean by fracture? Fracture is the material is going to break into 2 or more pieces if I further increase the stress. Okay, now, so up to point C, it is called as yield point. Okay, I will draw a point here, call this as some letter T. Okay, so up to this proportionality limit, the body executes the elastic properties. If you go beyond the yield point, it will enter into a plastic region. We already discussed what is plastic region. Plastic region is the one where the body will not come to its original shape or the size. Okay, even after the removal of the additional stress. Now up to this point, the body can execute the elastic properties. So this is still in elastic region, right? So here, whatever it has traced, this whole point O to T, it is called as epsilon, that is called as a permanent set. That means if you remove an applied stress beyond the yield point, you cannot trace back the body to its original dimensions. You have limit up to this proportionality limit up to point B. If you remove the applied stress, the body is going to regain its original shape and size. Okay, so if you continue to apply the additional stress, the body will reach its yield point. Each material has got its own yield point. This is very important in building structures. Okay, so every material is having a yield point. Okay, so beyond that yield point, the material is going to fracture. If you apply stress continuously, it will reach its ultimate strength and it will break into different pieces. That we call it as a fracture. Okay, so here, so whatever it is remained. So say for example at point C, I am going to stop the additional stress, the external stress, the body is not going to retrace back. Okay, so that is, we call it as a permanent set. The total, whatever the changes is occurred inside the material, that we call it as a permanent set. Even if you remove the stress, there will be this much permanent change remain inside the body. Okay, so after the point C. So up to here you can play with the material. Okay, if you remove the stress, the material will go back to its original dimensions. That is why you call it as a, it is going to show the elastic property, elastic region. Still it is in elastic region up to point B, up to proportionality limit. If you go beyond, it is not able to retrace back the same material as it is there in the original dimensions. Okay, now this will reach to ultimate strength. Fine. Then say for example, from ultimate strength you are again applying a stress. See how it is varying. So it has reached here O to A, it is linear change in the stress strain. Okay, here Hooke's law is valid only between point O to A. Hooke's law, point A to O to A exhibits Hooke's law. What is that Hooke's law? We already discussed, stress is directly proportional to strain. If you remove this proportionality symbol, how will write? Stress divided by strain. If you remove proportionality symbol, there will be some constant, okay, say K. So this is called as elastic constant. So this Hooke's law is valid only between the region O to A, because there is a linear change. How we say stress is directly proportional to strain? That means whatever the amount of stress you have applied on the object, the corresponding, there will be strain is also there. Okay, how they vary? They vary linearly between the point O to A. So only this region can exhibit the Hooke's law. So what happens after this point A? If I increase the stress, it is going to increase the strain as well, but it is not linear variation of the strain from point A to B. You cannot say that point A to B it holds good for the Hooke's law, right? Then if I further increase, it will go to yield point. From yield point, if I remove the stress, so this will end, the body will end point here. It has to supposed to end at point O. Since it has entered into a plastic region, it has ended at point T. So whatever the distance between O to T, this is called as permanent set. That means even if you remove the stress, there will be a deformed body you will get. Okay, there will be permanent set inside the body that you are going to obtain. Right? After the point C, you will see there will be a change in the region, elastic to plastic. Further point E, it shows you the fracture point. Fracture is nothing but the body is going to break into different pieces. Okay, each material has got its elastic limit. So I given an example, take rubber band, stretch it. Okay, it will extend it linearly, stretch it further, it is going to increase its length. Further, if you stretch it, it will cut into two different pieces. Similarly, it holds good for metallic wire. Okay, take metallic thin wire of a copper. So this is the phenomena which we can see inside the copper wire. Okay, copper wire, how its length is going to increase? We know that all the metallic materials are elastic in nature. Okay, for less deformation, low deformations. If the deformation is less, we can say that the Hooke's law is valid for metallic compounds. Okay, so we have taken a metallic wire copper. This is the trend, how the stress and strain are going to change. Stress is applied continuously, there is a linear change in the strain up to point A. Okay, so this is a perfectly elastic body. Okay, if you remove the stress at point A and B, the body will go back to its original dimensions O. Okay, but in nature there is no perfect elastic body is available. Okay, so perfect elastic body in the sense it has to regain its original dimensions 100%. Okay, you take whatever the objects you want, but there will be no perfect elastic body in nature. But there will be one material which is very much close to this perfect body, elastic body, that is if you mix phosphor with bronze. Okay, this material is somewhat very much close to the elastic body, right? But in nature there is no perfect elastic body which can show a perfect 100% elastic property. That means if you remove the stress, it has to go back to its original dimensions. So whatever it is there in the initial stage, it has to regain its original dimensions. But in nature, there are no perfect body, but it is very much close to that elastic body, perfectly elastic body. Phosphor mixed with the bronze. Okay, it can exhibit this Hooke's law, and it also exhibits the elastic properties. Okay, so why we are going to study the stress strain curve? It is very important in structural engineering. So the scientists, they want to know about this yield point. Okay, so for each material the yield point is to be calculated. We should know what is the maximum yield point and what is the maximum stress it can take. Okay, beyond that it is going to break into different pieces. Okay, so if we know the yield point, we can tune the materials based upon the yield point. Okay, so this is very important in structural engineering, yield point. Clear? So one more is that is we connected to this stress strain curve, that is strain hardening and strain softening. In strain hardening, we are going to increase the yield point. So this yield point can be increased in strain hardening, but in strain softening, in the sense some concrete or soil materials, if you take, how it looks like for strain softening, same strain curve, stress strain curve, if I take stress and strain, for strain softening the curve will look like this. Okay, which are the materials? As it's told, concrete or the soil. If you take, it will look like this, right? But we already know that. So in the strain hardening, we are going to change. In the strain hardening, so I'll show you somewhere here. Strain hardening. This is very important phenomena in the elastic materials. Strain hardening. Okay. If I draw the stress strain curve for strain hardening, what is that strain hardening, which is also called as work hardening? Okay. If I take this strain, it is stress, and this is the strain curve. So how it looks? Same thing. So here up to this is elastic point A, then it will be a proportional limit, then it is yield point. This you call it as B, this is yield point. Okay. Now this is original thing. Now I want to increase this yield point. So I have to unload the object from point C. Okay, point C is nothing but it is the yield point. Okay, we already seen here. This C is the yield point here. A to B, it is called as proportionality limit. Okay, so why you want to increase the yield point? So in order to increase the performance of the materials, we are going to increase the yield point of some materials. Okay, I don't want to break it down into fracture beyond this yield point. There are some materials which can show increased yield point once you stress it again. Okay, say for example, this is the yield point, C is the yield point, right? So if you unload or if you stop the stress, it will go back to its original dimensions. Okay, say for example, this will be a permanent set beyond this. Okay, if I remove everything, whatever the stress is applied, if I remove it, it will go back to original up to proportionality limit. Okay, if I stress it again, the same material I am going to stress it again. So how this curve looks like? Okay, I'll draw it here. This is, you call it as O dash. This is point A. This is proportionality point B. And this will be yield point. The earlier yield point is here. Now this is the increased yield point. Take the same material, unload it at point C, okay, or well within the point C, the material is going to regain its original dimensions. Okay, now again the same material, I'll stress it again, it is going to increase its yield point. Okay, so there are some materials which show increased yield point for the continuous stress, right? So these things are very important in order to study the structural engineering materials for various applications, especially this yield point. Okay, I hope all of you understood. Okay, thank you.